I'm very happy to be here. I'm a colleague of Carl and Jessica at Lund University. Short disclaimer to start with, I'm not a product efficiency researcher. I'm an economist looking at climate and energy policy, but I was called into this research project to do some also quantitative analysis and combine an analysis of minimum energy performance standards and carbon pricing policies. So, what is the connection of minimum energy performance standards and climate change? And Peter gave a couple of introductory remarks about that. I just have one quote here, that returning warming to below 1.5 degrees centigrade, which is one of the Paris Agreement targets, by 2100 becomes infeasible if final energy demand is not kept to very low levels. And the same is probably true for the 2-degree target. So we need drastic cuts or improvements in energy efficiency because we also need the energy to be used in other sectors. So energy consumption of home appliances is large and growing rapidly. These are just a couple of stylized facts here. While the best available technique or technology is often 30 to 50% more efficient than what MEPS currently require. These standards can reduce final energy consumption in the residential sectors by 20% in 2030, so there is actually potential. And as Carl in the beginning introduced, these standards for vehicles and appliances in the US are actually among the best performing climate policies, and also an evaluation of the Ecodesign Directive in the EU provides similar evidence. So there has been an impact of minimum energy performance standards on CO2 emissions. This is in a way remarkable because, at least from my understanding, it's not primarily a climate policy. So one rationale, I know there are many behind minimum energy performance standards, could be that, they direct technology change by forcing manufacturers into innovation and consumers into the adoption of this more efficient innovation, which should be in their own interest, as these standards aim at minimum life cycle costs for end users. And we heard, well, this is not the only way to set them, but still it's one of the main objectives to actually reduce also costs for end users. But, a big but, energy consuming appliances cause also external costs, not just costs to the end user, but to society in the form of CO2 emissions through the generation of electricity. And these external costs are, from an economic perspective, summarized in the concept of the social cost of carbon. So what is that? I think this is the most common term used to describe the value, the monetary value of the climate externality. And to be perfectly honest, there's little scientific agreement about the specific size of this externality. And estimates differ between a few dollars to several hundreds, and more recently maybe even thousands of dollars per ton of CO2. Again, we heard in the presentation before that, yes, economists often see standards critical, but pricing instruments very favorably. So in theory, carbon pricing is considered the first choice policy to internalize the social cost of carbon. But in practice, we have seen that these carbon pricing policies that are implemented around the world are insufficient to reach climate targets. There are too few of these policies, they cover not enough emissions, and the price incentives is way too low in many cases. So now our idea was, maybe we can see how the minimum energy performance standards can capture this social cost of carbon. There was an idea developed by Jessica and Robert van Buskirk in the US and Carl, and I joined the team later on. So marrying the social cost of carbon with a MEPS concept. And the first idea we had, well, let's integrate this cost into the modeling of life cycle costs. So it actually affects the price component in the life cycle cost of an electric home appliance. And this might then shift the optimal, the least life cycle cost point. And I will get back to that. But we also turned around the perspective and asked the question, well, what kind of carbon prices would be needed to mimic a very progressive and ambitious minimum energy performance standard? And I will talk you through these two perspectives on this integration of social cost of carbon and carbon pricing with minimum energy performance standards. Unfortunately, we didn't use dynamic data, but we had a snapshot in time. So we looked at the UK market for home appliances in 2016. That's where we had the data. 4 appliances were included in the study: refrigerators, dishwashers, tumble dryers, and TVs. Now the first thing, include social cost of carbon in the life cycle cost modeling. Well, life cycle cost consists of 4 components here, which is the appliance price to start with, but then we have the running costs over time, which consist of the unit energy consumption, the annual energy consumption on average over a year, the electricity price in the respective market, and then something that is called the present worth factor, which basically says, okay, how much of the future use of this appliance in the future do we consider in our analysis? What we had from the data set is the appliance prices and the unit energy consumption. And we adjusted it to the different features, because you have televisions of different sizes, you have home appliances of different sizes, so we adjusted with a regression analysis. When it comes to electricity price, well, we took the UK price, the most current estimate that we got there, and then importantly added this social cost of carbon component. If it is 15 pence per kilowatt hour, we added then the social cost of carbon that we used in our analysis, $150 per ton, which is very high, but we used a very high value to cover most to open up the range of current estimates, basically. And the emission factor of our electricity generation, basically saying how dirty is electricity generation at the time of our study in the UK. The present worth factor, well, we looked into literature to check, well, how long, what is the lifetime of the different appliances. So we found values ranging from 8 to 15 years, and then we discount that with a social discount rate, because not everything should be included in policy analysis. We used a social discount rate because we're in policy evaluation. If we look at what consumers actually do, we will probably use a much higher discount rate, because nobody considers the whole lifetime of an appliance when he or she is purchasing it. But for policy analysis, we thought it is good to use the official UK social discount rate from the Treasury. So what did we find? We found for refrigerators, so this graph shows basically average appliances in the different efficiency classes, A+, A++, A+++. In brackets is the consumption of kilowatt hours per year, again the average consumption of this market data, and then we have 3 curves. The black curve shows just simply the appliance price in the respective classes. The dark gray curve shows the life cycle cost, not considering the social cost of carbon. While the bright gray curve then shows what we are really interested in, the inclusion of the carbon externality, the climate externality. And what we can see is not much. So including even this very high social cost of carbon in the analysis is not a game changer, right? You can see the curve turning upwards a little bit, but the order in the efficiency classes doesn't really change very much. Similar results we could find for dishwashers. You can see it shifts the line, it turns it upwards a little bit, but no significant changes. The picture is slightly different for tumble dryers, which might be due to the fact that they use much more electricity. And still have rather inefficient models on the market, where we see that the life cycle cost, the most expensive life cycle costs were for the most efficient product category. But when we include the social cost of carbon, it's actually the least efficient category that has the highest life cycle cost, if you include the social cost of carbon. Then, and that relates to Hans Paul's presentation this morning, we had televisions in the picture, ICT equipment, and we really didn't find this relation that more efficient products are more expensive. Rather the opposite. More efficient products, adjusted for different features of the product, actually cheaper. Then, of course, yeah, including the social cost of carbon doesn't change that. It makes it just more extreme. They get even cheaper than before. To actually maybe give an input into the setting of MEPS, we also try to estimate by how much the life cycle cost optimum has to shift to account for the social cost of carbon. And we did that for tumble dryers and dishwashers, where our data fitted best the theoretical concept behind it. The theoretical concept is a little bit complicated, so I won't go into detail, but basically we assume that the life cycle cost function has a U-shape, close to the life cycle cost minimum. And that makes sense, right? If you want to reduce energy consumption almost to zero, you will have to put a lot of effort into it, which will make the product very expensive, so high up of the U. Then slowly, it gets less expensive and you have the energy savings kicking in. And then for the least expensive products, the product price might be very low, but then the running costs are very high. So this explains the U-shape. And then actually we have a formula also for calculating, based on this first formula, the shift of the life cycle cost optimum if you include the climate externality. So what did we find? This is the life cycle cost optimum without the social cost of carbon included. And we can see that, of course, we have even products that are not exactly on this line, because we try to fit a line to the market data that we have. If we then calculate how much it shifts, we see it does shift a little bit, but it just shifts by 25 kilowatt hours per year, this optimum. What I find remarkable is, well, yes, we can try to fit our curves to the data, but we should also not forget the single data points. That's why I included this gray box here, which shows basically all the models in the data set that have cost-effective efficiency potential and are already on the market. So while this fitting of curves helps to find an optimum for the whole market on average, we can also look at sort of the extreme values, right? This is almost a win-win, moving from the cost optimum to the bottom left. For dishwashers, the implied shift by including the social cost of carbon is even much smaller. So what we can say is that minimum energy performance standards can easily account for the climate externality.
Sorry, can you re-explain the grey box compared to the curve? Because it's I'm sorry, for me it's not, I think you made an important point and I'm missing it.
Well, the right end of the gray box basically shows where currently the unit energy consumption is, the annual energy consumption that is associated with the lowest life cycle cost. Yes. But we find products on the market that are to the left of it, which means they have an even lower unit energy consumption, annual energy consumption, and have lower life cycle costs. So while we try to find the statistical optimum, that doesn't mean that there aren't individual models in our data set. They actually better on both parameters.
So for example, for us, it would mean that the A triple plus product, for example, will still have an upfront cost which will not be that high, and that...
No, this is life cycle. Sorry, I was also a bit sloppy introducing this graph. It's the life cycle cost. That might imply that the upfront cost is still higher, but the energy saving overcompensates for that.
But my point for us, it would mean that the product in the highest class, so with is not that expensive, meaning that what it can save through is lifetime is more than the additional cost of buying. Okay, so that's because that would make it very clear for us what it means. Thank you very much.
Okay, with these results, I was a bit disappointed, and that connects to Peter's presentation, that I also feel the urgency of the climate challenge, and I think minimum energy performance standards can maybe do more. So what we then also checked is, what if we set much more ambitious standards, shifting the market by a whole efficiency class up? What would be the carbon price to incentivize a similar shift? And that's, again, a big equation, but basically what the equation says, we equalize the life cycle cost of a less efficient and a more efficient energy class, and try to find at which carbon price do we get equal life cycle cost. That's what this slightly difficult equation shows. And these results are in the middle of this graph. So this graph shows for refrigerators the carbon price that is needed to incentivize a shift from A+ to A++ in the lower part, and A+ to A++, 2 classes up, in the higher part. And the middle values show this. So 180 Great Britain pounds per ton, 550 pounds per ton, which is much higher than any carbon pricing scheme that is actually in place. What we did then on top of that is to do a sensitivity analysis to see, well, we looked at the specific market of the UK, but there are other countries that have either much higher, much dirtier grids, much cleaner grids, much higher electricity prices, lower electricity prices. So we looked at maybe we can come close to a range of carbon prices that is more realistic. And to be perfectly honest, we couldn't. So the bottom left corner of this graph is the closest we could get, but these are also extremely unrealistic assumptions, meaning that the electricity price is much higher or the emission factor is much higher. This could maybe be true for parts of Germany. And this is just one shift for one appliance where we somehow get close to actual carbon prices. Interestingly, the black line shows the dotted black line with the large dots, the present worth factor. And this you can understand maybe as an indicator of how rational a consumer is. With 100% present worth factor, we almost take into consideration the whole lifetime of the product. But if we move to the right, we consider less and less of the lifetime of the product. And if we take that into consideration, you can see that there's exponential growth of this curve. Then the carbon price is needed to incentivize a shift for less rational consumers. It's getting even higher and higher. Good. And as I said, this is the closest we could get to current carbon prices. For dishwashers, you see the scale on the left-hand side. It goes up to 2,500 pounds a ton. We're way off from current carbon pricing scheme. And the same is true for tumble dryers. Okay, what are the implications of this? So this is a very exploratory study and would be interesting to follow up with a more dynamic approach, because we have a snapshot of one market at one moment in time. But still, I think we can make some policy conclusions or derive some policy implications from this. First, and I said that already, the climate externality of home appliances can be easily captured by minimum energy performance standards that are not even much more stringent than those that are currently set. Ambitious standards can achieve efficiency improvements and corresponding climate mitigation that cannot realistically be incentivized by carbon pricing. And if we take into consideration the presentation we just saw online before, that actually quality adjusted prices almost went down. So we got a quality improvement at the same price level. So if we consider these dynamic effects, it means we have a cost-effective mitigation option, efficiency in home appliances, that cannot be achieved by carbon pricing against the promises by economists who say, well, if the marginal abatement costs are just low enough, people will buy into it. So we could show that. And I think there was an ECEEE workshop in November last year here that actually just was on these behavioral aspects of investments into appliances and what keeps consumers from investing. And I think, and again, connecting to Peter's initial presentation, the best time to apply these stringent standards for climate change mitigation purposes is really now, because the electricity grids are still sufficiently dirty to make an impact. So if you look at my home country, Germany, they now have the plan to have renewables 65% in 2030. This is not so far from now. And then, of course, the mitigation you can achieve by more efficient appliances is getting smaller and smaller and smaller. And I think, and I'm really not an expert for that, but there is still large efficiency potential. Okay, I want to close with a short quote from one of my colleagues and friends, Peter Hennecke, with whom I edited a book from the Wuppertal Institute, who said it's a sustained delusion of energy policy that efficiency improvements can be realized by the market and sovereign or rational consumers alone. So I think just to debunk this claim that is made often by economists that carbon price is enough. Well, it's not enough, because we have to realize that consumers are not the utility maximizing rational agents, but they have behavioral particularities. Thank you.
Hello, Stefan Arditi from the European Environmental Bureau. Well, thank you very much. I think it's very interesting exploration. And honestly, I'm a bit disappointed with the result. I would have preferred that we can take into account the carbon price in setting the maps. However, I think there is this tendency that the grids will be cleaner and cleaner. So as you've noticed, so it may be not a way to go forward. But today we are considering also resource efficiency criteria. And there it might be, and we clearly lack evidence on that, that the embedded carbon in the material we use to manufacture the product, it is more or less captured today through the analysis and what we call the preparatory study during the I would say the setting of measure. But could we try to assess exactly the same thing if we were reflecting, you know, the saving links to the embedded carbon in the materials used for the product, as it may help us to justify why we could move in that direction as well. And of course, it could better bridge, you know, this material efficiency with the climate, and in a way enhance the link we can make between eco-design and climate change mitigation. Thank you.
Yes, and I think we will discuss that question very much tomorrow also in one presentation. I think for this particular study, it would be relevant if there's a huge difference in embedded carbon between more efficient and less efficient products. I haven't actually seen a study into that. So maybe there is one, so we just haven't seen it. In that sense, the embedded carbon doesn't affect these results unless there is a systematic difference between more and less efficient products, which there might be. I was also not fair to carbon pricing. I don't think it's either or, it's complementary. So because that was your opening remarks. I think, of course, why not? I think I see MAPS as a way to make carbon pricing scheme like the emissions trading more efficient, because some of the sort of low-hanging fruits or fruits lying on the ground are actually captured and people are forced to use it. The economists say, yeah, the system will capture them anyways, but we have all kinds of behavioral failures and market failures that lead to a situation where they are not captured. So I think there is a good argument for coexistence of the two policy instruments.
Sorry, I don't want to monopolize the word. I just want to be clear on what you answered to us. You said that you haven't noticed any difference, major difference between product in terms of embedded carbon. But I think also for us, it's because so far we haven't set, I would say, stringent requirement or a labeling or a dynamic system on it, which means that manufacturers were not necessarily interested in making this difference. But today, if we take like short life products such as, you know, ICT or things with a less, you know, a shorter lifetime, it might be that if you use, you know, if you place on the market a product that can be optimized in its power supply without changing, you know, the material, then you will create this major difference. And in a way, if you could investigate in that direction and give us some evidence that, in a way, we are not doing something completely useless and stupid when we claim that, that would be good. And, of course, if you can also say, but in fact, guys, you are doing something which is not so good, it's not good news, but at least we will then start investing our energy somewhere else.
I just recommend come back tomorrow, because we will have one presentation on almost exactly that topic to see under which scenario, in which electricity grid does it make sense to extend lifetimes, when does it make sense to have shorter lifetimes. It's just not my specific research area.
But you should do this, Jonas.
Thanks for the interesting presentation. It might be that I'm a bit rusty on my least cost analysis, but you showed a few graphs where the current least cost would be around the A+ energy label, and it seemed to be more expensive than to get A+++ for a consumer. And if you were to add the social cost of carbon you would end up having a dip around the A+ label rather than at the A++ side of things. I think it was on dishwashers at the very least. You have, with the B label, it would be more expensive for consumers, and at the A++ side, it would also be more expensive. And then you kind of find this optimum in the middle. Is that then kind of pushing all consumers onto the A+ product? That would be the idea? Or if you understand what I mean, is that kind of forcing all consumers into one price category if you add the social cost of carbon? Or could you also keep it open for all price categories if you start to add the social cost of carbon across?
And then it depends.
Maybe the example
I think it depends on your
dishwashers,
policy priorities first. So if you want to have effective climate policy, you should nevertheless try to push everybody as far up as you want to. If you want to have sort of consumer protection policy, so least life cycle cost, plus a bit of climate change externality capturing, then maybe what you said is right. But I also want to point out that this is, again, a snapshot. So what we heard before is that there is a dynamic change in prices. So once you regulate, sort of you cut off the least efficient products, then the market reacts and also prices change in the more efficient categories. So this is a shortcoming of this study that we didn't look into that.
So Jonas, will some economists, will they change their mind, you think, if they see these results?
I hope so. Well, I have to say, sometimes we're creating a straw man. I think many economists that I have talked to are very aware that carbon pricing has its shortcomings, and there are market failures and behavioral shortcomings that have to be taken into consideration. So I think this is entering more and more the mainstream. I'm not sure whether this mainstream is already very visible and salient in policy making. That's another question.
Jonas, I think it's a very interesting presentation, especially regarding the relation between, as you said in the beginning, the pricing strategy and the MEPS. If you could go a few slides further down where you show the sensitivities.
Yes.
Because this is, as you said, the 50% is maybe what, say, real consumers, if we can call it like that, if you take into account real consumer behavior. And what you show is indeed the carbon prices that are needed then to change behavior. And I think this is exactly what the mechanism is, that due to all kind of circumstances and factors, people indeed, they react to prices, but only when they are increased very, very much. And long way before that, and we see it not only with consumers, but also with industry, long before you reach that situation, politicians stand up and cry. The industry says we are going to be bankrupt, we're going to be outperformed by others. So that clearly means that on one hand you could say indeed if you have the prices high enough, it certainly will work. On the other hand, you will never get into that situation because there are other mechanisms which are also real life that prevent that. So for me that is the most say convincing reasoning that prices alone are not say not a real world policy.
Yes, if I can also just briefly comment on that, I fully agree. I also think this is a very economic analysis. If I would do a psychological analysis, you probably would see effects of price changes, drastic price changes. That doesn't mean that suddenly it becomes attractive from a life cycle cost perspective for consumers, but the price of energy is suddenly so salient, so visible that consumers nevertheless react, even though it doesn't make economic sense for them. So yes, this is the economic view on it, and it shows, well, from an economic perspective, we cannot convince rational actors. But there might be situations where we can maybe have a small impact by price changes, but yeah, through another mechanism.
Thank you. And I think we also know when it comes to increasing the Swedish carbon tax or squeezing companies more in the emission trading scheme, we know there are talks of carbon leakage and them moving, whereas if we regulate their products, they still want to sell them in Europe. So there's a different dynamic there for sure. Good, thank you.